So I think my volume is a little low today on the microphone. I'm having some technical difficulties trying to turn that up some, and I may be able to do that in the future. For now, I'm just going to speak closely into this. Hopefully there's not a lot of clipping or other weird noises. But this is the climate slideshow I wanted to talk about, including some of the causes of climate changes, both natural and man-made or anthropogenic. Anthro, human, gen, as in Genesis, originating, different ways that we classify climate, and so on. Again, climate is not the same as weather. It's a long-term average of weather variations. So, in general, we would say that even though Nashville has some pretty wild weather changes, it is a temperate climate because its average over many years is kind of neither a very hot tropical climate nor is it a more boreal or polar kind of climate. So all of these kind of give they're very evocative of different climates, right? So here, this swamp here, remember it's a swamp because it's got trees and it's a wetland. This swamp here kind of gives you this idea of a lot of precipitation, as well as probably temperate temperatures, maybe subtropical, but contrast that with this tropical rainforest here, and with this almost more boreal forest here that's much colder. This is obviously very dry, even though there's water back there. This is a low precipitation area that's just an oasis. This also looks very dry, but that's definitely a different climate than here, right? In fact, this also is probably rather dry, but there's kind of standing snow everywhere because of the difference in temperature compared to a place like this. Climatology is just the study of climates. This says it's a relatively new field. I mean, people were aware of different biomes for a long time, but people didn't start applying quantitative kind of understanding to these until really the second half of the 20th century, when we started to observe changes in climate and observe or make observations about, for example, the ancient past where climate was extremely different from today. For example, just a few tens of thousands of years ago, the Sahara Desert was a very rich green area. But of course there were more dramatic changes, like the very cold past of the Indian subcontinent, right, because of movements of the continents, or the Antarctic climate that was previously more temperate than it is today, of course. And computer modeling, more so than in a lot of fields, has really advanced climatology. The ability for us to model, for example, the locations of the continents in the past, and to take in a huge amount of data at once from all kinds of different weather stations across the world and average them in, milliseconds at longest, gives us a lot of power to study how climate is changing today and how it has changed in the past. Again, averages of temperature, precipitation, and other variables. Those are really the two big ones here. Wind speed, wind direction is also relevant, especially when we start talking about things like rain shadows on one side of a mountain, right? There, the wind direction becomes very relevant to the overall climate or the average precipitation. So again, this is weather, but when we calculate these, we are often using climate data combined with very recent weather data. But in general, again, weather is not climate. However, when we talk about climate, we often will use, uh, as I said, large data sets. Again, computers, very important for this, with generally any given climate source or climate study will use at least hundreds, if not in the thousands, of different locations, as well as, of course, different times, since we're averaging over multiple years. This says airport weather stations. See if you can't think about that for a little bit. I'll give you a second to pause this if you want to hypothesize. But basically, the idea is that this is important for the takeoff of planes, and these are open clearings, so it's easy to get good data in a flat, open area about, for example, wind. But as this says, this is going to be pretty different from the weather conditions in a city, and that's because cities are what we're about to get into in a bit here, kind of microclimates. They have their own distinct climate from the surrounding area. Generally, and this is a good rule of thumb to remember for a quiz, say, a climate is usually at least 30 years of data averaged together. And this gives us what's called a climate normal, or basically what is normal for that area. And as it says, weather might differ widely from the normal. So if we've got an Arctic blast that came in, for example, I was just remembering this from the late fall this year. Even though we had a really warm winter with all that rain, in case you have already forgotten, in like very beginning of November or something like that, we had some days that were like 10 or 12 degrees Fahrenheit. Excuse me. Those 10 or 12 degree Fahrenheit days were definitely different from the normals for Nashville. They were much lower temperature. But in general, this is what a climatogram looks like for an area or for a biome or for a city where you've got temperatures maybe represented as a high and a low average for a month, as well as precipitation. And this is going to be very different from place to place. This looks like it could be about for Nashville, right? Lows well below freezing, highs about around freezing in the winter, drier in the winter, wetter in the summer. Notice this is northern summer, northern winter. If this was Australia, right, it'd be the opposite, dip down in the middle. With April and May being kind of high precipitation points, but the summer being wet in general all throughout. Again, that's not for Australia, that's for this graph here. If we have a tropical rainforest, we would expect kind of the temperature to be pretty warm year-round because it's in the tropics, right? There's not strong seasons. Precipitation high year-round. If we are talking about India with a monsoon season, right, then the monsoon season would have big precipitation jumps there, and then the rest of the time would have lower precipitation. Right? You can expect to understand a lot of information, not just about a biome in general, but also how that changes over the year from a climatogram, and that's why it's pretty useful, even when we're not talking about how climate is changing over time, to look at. We're going to have to skip that. But the causes of climate, number one, latitude. So how far north or south are you? How close are you to the equator and the poles? Topography, again, that is kind of like elevation changes. So is this a high altitude place, a low altitude place? Is it in the rain shadow of a mountain range? Is it on the, is it near the ocean, or is it far from the ocean? Close to sea level, or as I said earlier, high altitude. And then air mass movements. Now this also can cause weather, but in general, if there's a yearly frequent air mass movement, or if there is a, for example, if we know we're in the polar cell, that's going to have a different movement of air where air is coming down from the poles. than if we are in the Hadley cells where air is going, again, towards the equator. So here we know about the unequal heating of Earth. Lower angle means less irradiation or less intensity of light. If the sunlight's directly overhead or it's close to a normal angle, then we've got higher intensity light. We've seen this before. None of this should be surprising. Again, topography, if we have different, like if we have a higher slope, then there's probably going to be less evaporation because that water washes down away from the area. If it's flatter or has more lakes, then we're going to have more evaporation. That means more cloud movement, meaning more precipitation. This shows the seasonal temperature change here for, I assume this is for northern summer, of course, because this is warmer, this is colder. Showing that on land there is a faster temperature change than in the water. That's both because the water has mixing of currents and, of course, because water just cools down and heats up more slowly because it can store more energy than the land itself. So the land tends to heat up more than the water does. Another example of topography, again, the rain shadow, classic example. We've already talked about rain shadows. Just refresh your mind on that or look it up again if you've forgotten how that works. Air masses, we've already talked about, or you have read about the different kinds of air masses. So we know that these air movements in general, these basically winds, will cause climate to move in different ways. So for example, here in Nashville, we're getting air that comes maybe up from the Gulf, but generally coming from the west. That means it's going to be drier, right, than if we were on the coast here, where it's coming from the west near the Pacific Ocean. And if we were in Florida and it's coming from the east and the Atlantic Ocean. This is just an interesting graph to look at that is air mass movements. If we actually compared this to surface currents on the ocean, we'd see that they're very similar. In fact, they're caused by the same things. The only difference, of course, is that there's a little bit of a kind of what we would call, I guess, a North Indian gyre. Again, in the ocean, there is no gyre here in the northern hemisphere Indian Ocean. It's just kind of too small to get that water flowing in the cycle that's necessary. There is the Indian Ocean gyre, South Atlantic, North Pacific, South Pacific. All very classic. And then here we have the kind of countercurrent right at the equator, as we do in the ocean currents, if you went back and looked at that same slide. And then this is the thermohaline circulation. Not exactly the same ocean current, but the ocean currents I'm talking about here would be the surface currents. But the winds are kind of the same. Actually, this is an ocean current diagram, isn't it? But the winds move in the same pattern because the surface currents are moved by the winds, of course. Gulf Stream, another example of just an air mass movement. It also brings water with it, both in the atmosphere as clouds and in the surface currents that it drives. So you all are probably aware that this is what kind of heats up Europe compared to the same latitude in Canada, right? Spain is fairly warm, whereas kind of northern U.S., much, much colder. Despite being at the same latitude, which is, of course, a difference in climate that we're talking about, not just weather. Based on all this, we can kind of classify climates into different biomes. This is usually credited to Vladimir Köppen, a climatologist in the early 20th century, kind of very early on, kind of trying to use climate science, or excuse me, climate data to define, as I said, biomes that were already kind of well understood to a certain extent. Arid, semi-arid are the dry ones. Tropical wet and tropical kind of moderate precipitation are kind of self-explanatory here. Mediterranean is referring to a specific kind of steep slope, seasonally dry climate that's very classic of the Mediterranean, right? It's not particularly dry in the air necessarily, but there's not a lot of precipitation, at least not in kind of a year-round sense. This is kind of the classic grape growing weather. Humid subtropical, that's what we're talking about for much of the southern United States, much of the Chinese lowlands, marine west coast is comparable to much of northern Europe, but is really defined from the U.S. west coast here. And then things like tundra in the far north, ice cap. Non-permanent ice is referring specifically to some of the lands here in the Arctic Ocean that basically melt in the summer, is what that's saying. But in general, we can classify them as tropical climates, mild climates, and arid climates, as well as things like continental and polar climates. Some of these have some overlap, by the way. Like continental, many of the continental climates are also mild climates. A microclimate is importantly basically a climate that is very different within a larger climate. So again, this can be as small as a few square feet. This is a garden bed. To a mountaintop that is going to be perhaps much more dry than the surrounding climate. Say it's, Mount Fuji or something. Top of Mount Fuji is going to be much drier than the Japanese lowlands surrounding it, right, where there's a lot more precipitation. A classic example of a microclimate, and I think probably the most important example, I don't know if that's shown in here. Yep, it is the city. Well, this talks about San Francisco, the kind of the Bay Area compared to all of California, but I'm actually referring to the specific microclimate known as the urban microclimate. It's very important to understand how that's different from surrounding climates, and a lot of that has to do with the not just the emissions of a city, which can trap heat in thermal inversions, like we've already kind of talked about, and I've had you read about, but also the fact that the asphalt has a very low albedo. It absorbs a lot of light that is not absorbed by, for example, grass or ice or anything like that, right? So grass absorbs a fair amount of light, but it reflects green light very well. The black asphalt of a city doesn't reflect green light at all. And so it's going to absorb a lot more energy. It's going to be a higher temperature in a climatic sense, not just in a weather sense, but in a climatic sense than the surrounding area. And so that creates a warmer microclimate in the area. This is just comparing a climatogram of San Francisco, California to Wichita, Kansas. We can see that Kansas has more stark changes with the seasons, being in a drier area, and the more consistent, humid area of San Francisco, much more consistent over the seasons. In general, we see that places with more humidity, because again, water holds that energy and stores it for longer. are going to be more modest in their changes over the seasons. The more humidity there is, the more heat it will retain in the winter, and the more cold it will retain in the summer, because it's kind of lagging behind. It's averaging out everything by acting as a big reservoir of energy. In a drier area like Wichita, we can get a sudden jump up in temperature in the summer, and a sudden drop in temperature in the winter. Ditto for Nashville, of course. I mean, some people say, "Oh, it's so humid," but I grew up in North Carolina. This is a totally dry place to me. And the climate science would not agree, apparently. Humid subtropical is what that's saying. I don't know that I'd really call us subtropical. Again, microclimates can be, this is talking about the urban microclimate again, with a heat island, because the asphalt and the glass and everything like that in downtown buildings will absorb a lot of energy that would be reflected elsewhere. Just kind of look over this stuff again. Thermal imaging of a city, you can see the roads are totally bright, bright white or bright red. So climate changes, I promised we'd talk about that. There are seasonal events that can change climates, or yearly events like El Nino. And then there are these kind of longer term ones, like the interglacial intervals and ice ages. Right now we are in an interglacial period, but ice age is kind of more the standard, the default state, I should say, for the planet. And these, please keep in mind that these occur, and even I kind of get this wrong sometimes, these occur much more frequently than, for example, the movement of the continents, right? An ice age is every couple of 10,000 years. Humanity has survived ice ages. Contrast this with the movement of the continents, and as long as humanity has been around, the continents have basically been the same. The continental movement is over millions of years or hundreds of millions. Ice ages over tens of thousands. We know about the seasons being affected by sunlight. El Nino is basically just a reverse in wind direction within a certain area. For a year, every few years. You don't need to know too much about it, although it's definitely a worthwhile read if you are curious. The basic idea is that it redirects air such that if we have El Nino, this air kind of diverges instead of being one smooth jet stream in order to create this kind of warmer area throughout most of the United States. Again, if we want to talk about a long-term climate event that's natural, we're talking things like ice ages. Here we have an increase in the number of, or in the amount of glacial coverage. So a lot of the oceans are being reduced to be put onto land as glaciers. That is going to increase the albedo of the Earth overall, make it colder, and so it's kind of this cycle that will increase until it hits a peak where there's a peak of glacial coverage, and then those glaciers start to melt again. I think because the ocean can hold less heat. I think that's what causes the reverse. Once the ocean can hold less heat, that heat starts to just kind of start to melt these glaciers again. Again, the ice ages are kind of the default, with glaciers covering about a third, or I should say ice, not necessarily glaciers, some of that sea ice, covering about a third of Earth. This is over the past 2 million years. So we can see that that has kind of been the normal state. As this says, there have been brief interglacial periods, inter meaning between the glacial periods, lasting 10,000 to 20,000 years on average. So we are in a interglacial period right now. The most recent ice age was about 85,000 years to 10,000 years ago. Definitely within the history of humanity. At this point, humanity had already left Africa and started kind of spreading around. In fact, because of the reduced ocean level, mankind was able to walk across the Bering Land Strait and, of course, enter the Americas and found the Native American civilizations. So this is about how far the glaciers went in the last ice age. Of course, we know that the Great Lakes are glacial lakes, so that's not a surprise that it went down south beyond the Great Lakes. This is just showing that, yes, mankind was around during this time. This was the last time that man interacted with the woolly mammoth, of course, which is now extinct, partially due to human hunting. And because, as I said, when there's more water on land, not sea ice, remember sea ice doesn't change ocean levels, but when there's more water on land, there's less water in the oceans, and so the coastline was further out. More of this was exposed surface above the ocean level. And in general, for the past 4,500 years since the last ice age ended, we've had a very stable climate, very warm compared to the past and compared to average over a long period of time. Then there was what is called the Little Ice Age from about 1500 to the Industrial Revolution in 1850. It looked like we were going towards a new ice age, and this would be pretty normal based on how we understand the cycle, right? The interglacial periods are 10,000-ish years, and that's what we're kind of coming up on the end of that. So it was thought that, okay, we're due for another ice age. This is probably the start of what was meant to be an ice age. But what happened in 1850? Well, we know that was the Industrial Revolution, and therefore the beginning of large emissions from fossil fuels, right? Will we get to that? When will we get to that, I guess I should say. Well, let's finish talking about natural causes of climate change, and then we'll talk about man-made causes here. But notably, much of what we know about climate comes from ice cores. These have air bubbles within them that can tell us about atmosphere at the time of the ice formation. Pollen, which will tell us about wind movements, right? Because we know where certain species live or lived at the time based on fossils. So if we've got pollen from a species of maple that we know don't live there anymore and only lived at the time of the ice's formation 450 miles south, then we know that something was blowing pollen from 450 miles south up to the north, right? Volcanic ash can kind of help us date things with major volcanic eruptions, but can also tell where wind is going, right? Other chemicals that might be in the air, maybe they're volatile organics, meaning things that plants release which would be kind of comparable to pollen, right? We can see what species lived in the area. I totally encourage you to watch this video if that link still works. I remember we watched it last year. I don't know if I found it on my own or what, but it's definitely a visible video. If you if this link doesn't work, you can search for it, is what I'm trying to say. We can also use tree rings that can show where there was a major disruption in a tree's growth, or lots of ash emitted or something. Fossils, we already talked about how that can be used. Radioactive samples, that can help us mostly with studying the movement of rocks due to erosion, for example. And natural climate change is either from various cycles caused by, for example, changes in the sun, changes in Earth's orbit, tilt and wobble, think precession, if you remember that word from a long time ago. And then, of course, the eruption of volcanoes that can cause ash clouds to occlude the sun, basically block out the sun for a certain amount of time. We don't need to go through these, but basically the sunspot cycles every 11 years. We know that there are connections from world temperatures to solar activity. I'm going to go ahead and preempt questions from certain somebodies. No, this is not going to be what causes climate change. We know this because we can correlate the data from the distant past, where the sun was undergoing the same cycles, to see kind of the effect of the solar activity. There is an effect, but that effect does not explain the variation that we observe nowadays with a sharp increase and an untempered increase that has nothing to do with an 11-year cycle or any of the duration cycles of the sun's changes. So yes, this will have an effect. That does not explain the effect of the current warming. Again, changes in Earth's orbit due to precession or changes in eccentricity. Again, these things happen on a many thousands of years cycle. Tilt varies, so we expect at the higher tilt the seasons are more marked than at the lower tilt. We're kind of right in the middle of one of these 40,000 year cycles. And then precession basically will just change as this at the other side of this cycle. Northern summer would be in December instead of in June, right? Over 13,000 years, that would flip, and then in another 13,000 years, it would flip again. Volcanic activity, we already talked about volcanoes in depth. We understand how they will interact with sunlight, for example. A Year Without a Summer from Mount Tambora. And then the anthropogenic global warming. The causes of these, how much do we talk about it? Okay, I might create a second video about the anthropogenic causes, and not all of these are causes of global warming. CFCs, for example, chlorofluorocarbons and aerosols are damaging to the ozone layer, which is a separate issue from global warming, although it does relate to interaction between the atmosphere and solar radiation. Anyway, look forward to that stuff next time.